Okay, so we're recording. So here's where we were last time. We were talking about vector fields and how you can view vector fields as representing, let's say, a fluid, right? And if you have a fluid that's flowing along, actually, let me make a better color choice here. I will go with the fluid. If you have a fluid that's flowing that you're representing with a vector field, a common choice is to represent the velocity, right, as being what about the fluid that we're going to represent with the vector field. So common choice, it's not the only choice, it's not even necessarily the best choice, but it is common. So we're going to presume that that's the case here, that the vector field represents velocity. And we went through this calculation last time, so I'm mostly going to wave my hands at it here. But the idea is that if the vector field represents velocity, then you can talk about in some given little amount of time, delta t, how much fluid passes through your given little area here. Whatever your little flat piece of area, area A, oriented by way of this unit normal vector, little n. And so you can just write down what the formula is for how much volume that is. And that volume, well, it's height times area of the base, right? Old high school geometry formula. And then that height you can think of as a component, which is a dot product. And then you can, there's a bunch of other little details in here. And ultimately what you find is that looking at now, let's see here, let me do like looking at this formula right here for delta V, right? And then divide by delta T, right? And what you find is left over is just this part right here, this expression right here, and this computes our flow rate, volume per unit time, this thing right here. And the term that we use is called flux. And we use the capital Greek letter phi to represent it. So neat fact, and the short pithy answer to the natural question, hey, how come we care about flux? Why would I want to take a dot product of a vector field with a unit normal and multiply by an area? Well, because that computes volume per unit time of your fluid flowing through your surface. That's why. So very important calculation. We're going to be doing tons and tons of stuff with flux when we get into, especially chapter 7. I think we'll start touching on it in chapter 6 a little bit. Okay, so neat thing to know. Now, the next observation I want to make, and we talked about all that last time. Next observation I want to make is about a related but different scenario, and just for distraction purposes, let me get rid of all of the coloring there. So what would happen if I changed things around a little bit and did not use the vector field to represent velocity? What if I, seemingly weirdly, used the vector field to represent, of all things, density times velocity? Seems a little weird. So if I were to do that, in that case, a reasonable question to ask, well, what does flux represent then? Right? Does flux represent volume per unit time? Well, certainly not. No, we've got an extra factor in there of density. What I want you all to work on yourselves, and I'm going to show you approximately how to do this, but I think it's a healthy exercise for everyone to do on their own, is show that this thing called flux in this scenario, instead of computing volume per unit time of fluid, it computes mass per unit time of fluid. Right? Now, also really important, important for application, sort of obviously, right? Because very often when we're interested in fluid, we're interested in not how much space it's taking up, but how much of it is there, right? So the fact that flux that we're going to learn a lot of great things about and learn how to compute and be able to study and do awesome stuff with, the fact that it computes this very natural thing of quantity per unit time of fluid is why this seemingly weird choice of multiplying density times velocity, again, seems weird at the outset, why that is a good thing. It's a good thing because it makes stuff we can compute relate to stuff we want. Does that make sense to everybody? All right. So how are you going to show this? And the answer is pretty much right here on the screen. You're basically going to copy this calculation, except instead of computing volume per unit time, right? We're interested in computing mass per unit time, and so you're going to start off by putting mass right there. How are you going to figure how much mass there is inside of this little parallelepiped? Well, it's the volume that you already have formulas for how to write down and how to develop times density. So you're basically going to insert a factor of delta everywhere in this calculation, and then that's going to get absorbed into the vector field. You see there it is right there at the very end of the calculation. So that's the very broad strokes, and I do hope that everyone will take a shot at that, healthy exercise, and will make sure that you are fully digesting all the details that went into this calculation. Okay. All right. Cool. This next page is kind of supplemental. I do think it's a nice thing to have in here. I'm going to go really quickly through this, and I'm going to basically skip the example at the end, which is a luxury that I like to have time for, but when I don't, it's really not necessary. So I just want to point out, not all fluid flows have this feature where I can talk about the velocity of the fluid. Sometimes it doesn't work like that. So my favorite example of this is, suppose you have 2 point light sources, right? So here's a point light source, and here's another point light source. Think of them basically as little LEDs, right? Little light bulbs. Each one of them, being a light bulb, is emitting photons. Photons are kind of a fluid in a way. Again, it's not wet, right? But it's a bunch of teeny tiny little particles that all kind of flow in some sense kind of together, at least we think of it that way, right? So kind of like a fluid. How would I represent, if I had 2 point light sources, as in this picture here, how would I represent that fluid flow? And the problem is, if I want to do so at, let's say, a point like this one right here, at that point, there's a couple of different velocities to keep in mind. Photons that come out of that point light source are going to be going that way, right? And photons that come out of this point light source are going to be going that way. So how do I talk about the velocity of the photons at this point? There's 2 different velocities. Problem, right? So there is a nice way to think about this, and roughly speaking, the answer is to use our existing computation of flux and how that relates to quantity per unit time of fluid. So we've already talked about how if you have a flat area, again, it has a scalar area, and it also has an orientation, how it's sitting up in space. And very often, if you have some little piece of area and you want to talk about how it's arranged or sitting in space, we use a unit normal vector to talk about it. It's very convenient that one little unit normal vector helps us understand the arrangement of an area in space. It's very convenient. And so here's the thing. Normally, or on the previous page, we use our understanding of velocity, or density times velocity, to compute flow rates, right? And I'm just going to turn it around. And I'm just going to say, look, empirically, I can get out there and measure these flow rates. Quantity per unit time of fluid flowing through whatever areas. And if you can empirically measure that, then that allows you to talk about a vector field that would give that answer, that empirically observed answer, by way of the usual flux formula, right? And so this is how we actually define a flow, a vector field representing a fluid flow in cases where there is this kind of, the photons are actually going multiple directions. And by the way, if you think about it, this two-point source question that we considered is about the simplest possible version of this. In our room that we're standing in right now, there is a much more common and much more complicated version of this, and that is, notice there's a ton of light sources, right? There's the projector, there's bouncing off the screen, there's light bulbs in the ceiling, and then, of course, there's light bouncing off every other surface in here. So if you look at any given point in this room, the photons are going every which way. You couldn't begin to talk about either the velocity or density times velocity of photons in this room at a given point. It doesn't make any sense at all. But you can totally measure, I mean, if you had the equipment, right? You can at least talk about, okay, yeah, but what is the actual flow rate of fluid, flow rate of photons through any given area, and then reverse engineer the vector field. Okay, so that can be dealt with as well, is really kind of my punchline here. Okay, this is a really cool example. I'm sorry we don't have time for it. I do encourage you to take a look, and there's some really neat ideas in there, and there's kind of a cool answer, but it's a luxury that we just can't really quite afford this year. Okay, all right. So next I want to talk about something called flow lines. Really ought to be called flow curves because they're not necessarily straight lines, but whatever. The idea is that if you have a vector field representing a fluid, and let's suppose that in this case the fluid is actually doing not so much like photons, but much more so like water, where at any given point there really is a well-defined velocity. Right? If you were to drop I'm going to call it a particle, by which I mean some small little thing that doesn't sink to the bottom and it doesn't float to the top. It just kind of has the same density as the water itself. What's that little particle going to do? It's going to go exactly where the water tells it to go, right? If you drop I'm going to just say a leaf into a river, right? And the water's flowing that way, the leaf doesn't go on its own in some other direction. It goes right with the water, doesn't it? Right. So, all right, well, if that's the case, we can actually write down equations that describe the path of that particle. And it's not even really particularly a deep observation. It's surprisingly almost obvious. And the way I have it annotated here, I think illustrates that. If you want to know what the velocity of the particle is, what direction and with what speed is the particle moving, well, the velocity of the particle is equal to the velocity of the fluid, right? I mean, that's what, as we discussed, I mean, the particle sitting there in the water, if the water is flowing, so is the particle. It's going right along with the water. So the velocity of the particle is equal to the velocity of the fluid. Now wait a minute, the velocity of the fluid may be going various different directions in different places. So if I've got a particle here, and I want to know what velocity that particle is moving with, and I say, yeah, well, it's the velocity of the water, I mean the velocity of the water at that same point we're at. I don't care what the velocity of the water is over here. Right? That's got nothing to do with what this particle is doing. So the velocity of the particle at the location where the particle is. Right? And if we're describing its location with a parametric curve, then that parametric curve is its location. So there you go, and the nice punchline is we end up with what's called a system of differential equations. Now, y'all may or may not, probably not, probably don't know how to solve these kinds of differential equations yet, but you will when you take Math 353, if you take Math 353 or 356, depending on your major. They'll talk about how to solve differential equations of this sort and thus find our formula for the position of the particle and thus telling you the answer to the question, how does that particle move? And this is called a flow line. Again, I wish it were called a flow curve. Everybody all right? Now again, we don't know how to solve those equations, but we can confirm existing solutions. And so that's what we're going to see in this example here. Y'all may recognize this vector field. This is the one where the fluid is kind of sort of flowing counterclockwise around the origin. Right? We drew a picture of this. And so the fluid is just kind of doing like this. And now our intuition, I think, right? If the fluid is kind of going around and around and around, what's a particle going to do if you drop it onto that surface of that liquid? That particle is going to go around in a circle, right? We would expect then for the flow line to be that, or a flow line, depending on where you drop the particle. And this is something that you can directly confirm, and I think everybody should do this. You should take this formula for this flow line, this candidate, speculated, right, flow line, and plug it into the equation, right, keeping in mind that this is your x, right, and let's see color choices. This is your y. Take those formulas, plug them into here, and confirm that sure enough, it satisfies this system of differential equations. Yeah?
Is there a way to derive from the right?
Oh, yeah. So the process of taking the system and finding the solution, that's called solving the system of differential equations, and that's what I'm claiming that I don't think y'all that y'all haven't seen before. And there is a way to do it, and it's one of the topics in Math 353 and Math 356. Yeah, and it's too much to go into here. Yeah. Okay. All right. So we've seen various different examples, physical examples at this point of physical phenomena, important natural physical phenomena that we modeled with vector fields, right? So we've seen vector fields used to represent forces like gravitational forces and electric forces and stuff like that. And we have also seen vector fields used to represent flows of fluids. That's what we've been talking about so far this morning. So one thing I've noticed in teaching multivariable is that a certain number of students will look at these two different metaphors, you might call them, like physical examples of things that represent the mathematical object we're actually interested in here, namely vector fields. Pick one and then just say, okay, I'm gonna hitch my wagon to this horse right here, right? And they're gonna go through the entire rest of Math 219 thinking of vector fields as forces, or go through the entire rest of this Math 219 thinking of vector fields as representing fluids. And there's a really big problem with this, and it turns out, we're going to see this in chapters 6 and 7, 100% we're going to need both. Right? If you are not comfortable with a vector field as representing fluids, then there are certain parts of chapter 6 and 7 where you're just going to not have the slightest idea what's going on. Right? So, and likewise with forces, certain things in chapter 6 and 7, you have to think about the vector fields as forces. So please don't make the mistake of making a choice between these points of view. You really, really, really need both of these points of view. Okay. All right, how we doing? Is everybody all right? Okay. So section 3.4 here, this is kind of a weird section. It's arguably really premature. What we're going to be talking about here in section 3.4 is really kind of chapter 6 and chapter 7 stuff. So why are we doing it in chapter 3? Pretty reasonable question. And the idea, well, first of all, because the book's doing it. Right? But also, these are some weird ideas and it takes a little time for them to kind of sink into your mind, and having a preview, however hand-wavy and unjustified this presentation is going to be, having a preview and kind of sometimes knowing what to expect when we get to chapter 6 and 7 is helpful, right? So as I just confessed, the discussion I'm going to give you here is going to be extremely incomplete. And I'm going to kind of wave my hands and say, trust me, a couple times, right? And we'll clean it up later. Okay, so y'all remember the gradient, right? Neat things that we know about the gradient. Here I'm writing it just as an algebraic thing. Here's a different way to write the gradient, right? And that's just notation, really, but you could imagine if I were to separate out a, air quotes, vector consisting only of partial differential operators, not partial derivatives, right? But just this is not partial of f with respect to x. This thing here is just the act of taking a partial with respect to x, whatever that is. Right? But if you grant me that flexibility, you write this down and you write the f next to it, you probably would understand that what I meant was this. Right? Is that cool? Right. So this is actually a really useful thing. And this thing, which naturally we associate with that little triangle symbol, is very handy in many other ways. So this is worthy of a name. This is called the del operator. Notice it is not called the gradient. The gradient is what you get when you apply the del operator to a real valued function. We're going to be doing other things with the del operator. So we can't use the same name for the operator and a certain thing that I might do with it, right? That just doesn't make any sense. So heads up, this little upside down triangle should not be referred to as gradient. It is the del operator. And y'all have seen me write down symbolic nonsense before, so I hope you're not, at least I hope you're not surprised by this. It is a little weird, but hopefully not surprising. Okay, so now that notation established, we're going to talk about a new construction here. It is called divergence. This is the formula for divergence. Notice divergence is something that you do to a vector field. Vector field consisting of coordinate functions, f1, f2, and f3. And notice what it is it is the sum of certain things you get that you do to those coordinate functions. And what is it that you do to them? Well, what you do to them is apply an x partial to the first one and a y partial to the second one and a z partial to the third one. And now I appeal to your notational flexibility, right? That this expression here, this weird formula that I've pulled out of thin air and that you have no idea why we would be interested in, right? Looks like a dot product, doesn't it, right? I claim that I think anyway, looks just like a dot product of our del operator, x partial, y partial, z partial, with our vector field f, f1, f2, f3. Is that cool? Kind of weird. So this expression is going to be useful. We'll talk about what it looks like geometrically in just a moment. I do want to point out that there are two different ways to write it. You can call it the divergence of f. A lot of people will write like div, div, right, with the understanding that it stands for divergence, and we'll write div f. Very common in math courses, for example. My experience in physics courses was that far more common is for people to write it as del dot because of this little convenience, and this is really handy in a lot of ways. So heads up about this. You'll see it written as del dot. By the way, I do want to throw in a quick comment. This is partly motivated by some things that I'm seeing on the exam as I'm grading the exam. Some students are a little casual, a little too casual with notation. I want to emphasize, if you want to talk about a dot product, you've got to put the dot in there. That dot is important. If you just write del capital F vector, that's not a thing. So the dot is really, really important. And likewise for all dot products, you can't just write two vectors next to each other. You got to put the dot in there. Keep in mind there are two different vector products. So if I see two vectors right next to each other, it's not clear which product are you talking about. You talking about dot product, cross product? Could be either one, right? Okay. So, what does it mean physically? Right? What does this look like geometrically? Here's where I'm going to have to do some hand waving, and we're going to justify this later, right? So loosely speaking, I'm going to say this thing called divergence represents how much the fluid is flowing sort of generally sort of outward away from wherever you are evaluating it. So to what extent do you have what you might call something that looks kind of like this? This is a great example of what I'm talking about with divergence. You see how the fluid is flowing all sort of outward away from the origin. Does that make sense? So again, why does this expression relate to this? Oh, long conversation that we will address more fully later. But right now, I just want to plant the thought, let that be digesting, right, in your minds, that this is what this is kind of a foreshadowing, or what do they call it? When you get spoiler, right? This is a spoiler for chapter 7. Okay. Yeah.
So it's negative like inward flow?
Yeah. That's right. Positive represents outward, and negative represents inward. Yeah, totally. Right. Okay, so let's see that happen. And here is the algebra. And now we've talked about vector fields. I claim that this is what this vector field looks like. We did in a very, very, very similar example. We did sort of a two-dimensional version example of this last time, I guess it was. So does the divergence actually do what I claim here? And, well, here's my vector field, coordinates x, y, and z for the vector field, and now we apply the del operator. I've forgotten what color I used for it, but anyway, del operator, dotting in particular, right? And you can just compute these partials. They're super easy partials, and the answer is 3. So the divergence is 3, which is positive, and that represents an outward flow. Now, this doesn't prove anything, right? This is just a for example, and again, any justifications that we need for what I'm claiming, we'll have to wait till later. Is that cool? Okay, so something to be on the lookout for, something to be kind of chewing on. So let's see here. What does this mean? And what does this represent physically? And there's a couple of different possibilities of what this could mean physically. There are a couple of different possibilities that are importantly different. And this is another thought that I want to plant that we're only partially going to develop later on. Again, this is a math class. We're going to focus on the math, and the physical, the nitty-gritty of physical applications is going to come in courses on those physical applications. So one possible interpretation you could make of what we're seeing here is maybe this represents a flow representing the amount of stuff near the origin decreasing. Right? So for example, maybe there's a tree full of birds. You know how when they're migrating, they'll all camp out in one tree, right? And then somebody sneaks up on them and says, "Boo!" Right? And they all scatter, right, as birds do. Well, as birds fly away, something along these lines, well, as they fly away, the number of birds in the tree is decreasing. Right? And so you could view this as being a representation of fluid kind of evacuating the area and therefore leaving less fluid remaining. Yeah? Okay. All right. Now here is a completely different physical metaphor for this. It could instead mean that this is a fluid source. Right? Light bulb. Easiest example. It could be a light bulb right there at the origin, and light bulbs create fluid, right? They create photons. Photons come shooting out of them and go every which way. So that would also create this picture. And if that's the case, the density is not decreasing. Right? Photon density. Light bulbs don't have a fixed finite amount of photons in there, and they lose their photon supply over time. That's just not at all how it works. Right? And then turning that around, likewise, if you've got birds flying out of a tree, it doesn't mean that we're generating birds. Right? So these are two totally different physical scenarios that could both be represented by the same picture. So, depending on the circumstance, one or the other of these interpretations might be more appropriate to what you're actually looking at in a physical application problem. And I just, again, want to plant the thought, be thinking about, as when we get into chapter 6 and 7 and we're thinking about these kinds of things, don't be too casual with your interpretation. Pick one and stick with it, right? Because you can get really confused if you start thinking about birds and then eventually you're thinking about light bulbs and you come up with silly ideas about light bulbs generating birds or something, right? That doesn't make any sense. Okay. Another example. Again, this doesn't prove anything, but this is just kind of this kind of tracks with the interpretation I'm making. Here's a vector field. Here's what it looks like. Again, good exercise to think it through. Persuade yourself that that's what that vector field looks like. You can compute the divergence with a couple of partial derivatives, and the answer ends up being 0. Now, again, I claim that this tracks, right? This calculation of divergence is consistent with the idea that divergence represents how much fluid is kind of emanating outward away from a point. So, for example, if I were looking in this general vicinity right there, and let's talk about how much fluid, whatever the fluid is, it doesn't matter. How much fluid is flowing outward out of this region. And from the picture, geometric appeal, it seems to me there's just as much fluid flowing in as there is flowing out. Right? So it kind of, again, tracks and makes sense that, net, total, there isn't any generally outward flow here. It's just as much in as out. It's just not net outward. Is that satisfying? All right. Next, object that I'm going to define and give no justification for. But again, that'll come later. So let's talk about a vector field F. And we're going to talk about what we mean by this thing called curl of a vector field. And this is a really weird one. It'll make sense later. We'll have good reasons to want to talk about this. But for the moment, mysteriously, I'm going to point out that this formula right here, strange though it looks, symbolic nonsense though it is, right? Again, you got to interpret as intended, right? Don't just kind of go with it, right? Notationally, and it's exactly what you would think it is. This thing here is an important object of the calculus of vector fields. That's called the curl. And then, of course, you quickly recognize that this thing is, well, I can see it's literally at least on a symbolic level, del cross F. Right? Because that's how we do cross products, symbolic notation. So, again, very handy. Again, you could write curl F. Perfectly reasonable. A lot of people do that. Much more common, though, at least in physics circles, at least in the early 1990s when I was a physics major, del cross F. Much more convenient in certain ways and much more common, at least in my experience. Okay, so again, we find ourselves in this situation where we're not really prepared to make any sense out of this yet, and that's the nature of what we're doing here. This is just preview. But what does this represent? How should I think about this? This is a harder one to answer. It's a harder one to even describe. This thing called curl, it represents in some sense, and you notice I put this in air quotes, it represents fluid kind of going around in circles in some sense. I don't want to say it exactly like that because it's really easy to accidentally say this in a way that's wrong. But here's my best shot, though, at how to make some geometric sense of this. If you have a fluid doing whatever the fluid is doing, and if you imagine a floating ball, that's, again, it's not floating up at the top and it's not sunk down to the bottom, it's just perfectly weighted. If that ball were in this fluid as you describe, would that ball be turning? And if it were turning, is it turning really fast? And if it's turning, is it turning around what axis? Right? So there's a difference between a ball sort of turning around like this versus a ball turning around like that. Does that make sense? Okay. All right. Okay, so an example. Again, here is a vector field. This is closely connected to a vector field that we talked about previously. This is kind of a three-dimensional version, if you will. Notice this is three-dimensional because this is defined in three variables, x, y, and z. Notice that whole kind of rotating thing that we recall from the negative y comma x that we saw in an older example. Notice the 0 here indicating that while it is kind of going around, it's kind of a stirred pot, if you will, in the horizontal directions. Vertically, nothing's happening. There's no upward component. So this is just literally a stirred pot, if you will. All the fluid is kind of going around like this. Is that cool? Okay, and here's my attempt to draw this. It's really hard. Drawing three-dimensional vector fields, give it a try. I think you'll believe me. Okay, so let's test the claim. Does curl, aka this formula, does it tell me an axis that this fluid is kind of rotating around? And in any sense, does it track with how fast things are sort of rotating? And well, again, you can just compute out that expression. You get 0, 0, 2, which you'll notice is a vector that points straight up. And yeah, that's pretty consistent with what we're observing in the fluid in a right-hand sort of sense, right? So the axis, the curl, if you point your thumb along the curl, right? And if you look at your fingers and how they sort of point around your thumb, doing exactly what that fluid is. So the curl vector points in the direction of the axis that the fluid is rotating around. Now here's just sort of a very approximate appeal. The magnitude of this, I'm going to claim, is in some sense that I'm not going to make precise. I don't want to get involved with units and friction and moment of inertia and weird thing. How fast would some ball actually be rotating? There's detailed devils in there. It's not our problem. But I'll just say this. If you were to throw a constant in here and make the vector field longer, representing a faster flow of the fluid, you would find yourself with a longer curl vector representing greater circulation. So in some sense, it kind of tracks with amount of rotation as well. How we doing? Again, doesn't prove anything. This is just kind of an example of what we're claiming curl does. Here is a different example, and pretty easy to persuade yourself, I think, that this is what that vector field looks like. And you can compute the curl of this vector field. Again, it's just details. Y'all can totally do that. And the curl is 0. And this suggests that nothing is rotating in this picture, right? And I think that's pretty believable. You look at it, again, imagine a little ball sitting in here. And that ball might get moved around, but this flow of fluid wouldn't make the ball rotate in any sense, right? Okay. All right, now before I get to the next example, I want to point out what is easy to misstate about what's going on in this example. It is tempting to think, oh, what this measures is the extent to which the fluid is going around in circles. That's not accurate. Curl does not measure the amount that the fluid is rotating. Curl measures if you had a ball sitting in here, how would the ball be rotating? And I know they sound similar, but it is different. And here is my example. Look at this right here. This vector field. Not hard to persuade yourself that it looks kind of like this. By the way, again, make sure you can think it through. It's, I guess step 1, make sure you believe this picture. Right? Step 2, make sure that even without the picture having been shown to you, that you can kind of think it through and put the puzzle pieces together and actually generate a picture like this on your own. Just thinking through what the formula does and what that means about the arrows, etc. Okay, so real quick, at a glance, do we feel like there's any circulating happening here? In the sloppy sense of the word of, is the fluid going around in any circles? No, the fluid, the flow lines, are all straight lines. So it's tempting to look at this and say, oh, no, there's no curl there because, look at the water is all going in straight lines. And that's just wrong. That's not what curl is. Curl is not about what the water is doing. Curl is about what a ball in the water would be doing. And now I'm going to appeal to your physical intuition. If there's my little ball, and if the water is flowing on that side of it in that direction, and it's flowing on this other side in the other direction, what do you think is going to happen to that ball? I think it's going to rotate, isn't it? Right? So this is a great example illustrating, again, this is a subtle thing, right? This, talking about what curl measures and how it represents a rotation of sorts. No particular particle of fluid has anything even vaguely rotating or even curved in this example. But we do have a curl. And there is a rotation intrinsic to this picture. It's a rotation of a ball sitting inside of the fluid. Is everybody okay with that? Yeah.
What is the meaning of the constant? I get that it's negative because you're going you're going clockwise, right?
Yep.
But in the other example, it was 2. And so
why
would it, where does that 2 come from? Because I guess the direction whether it's positive or negative,
Yeah.
rotation, I just don't understand the constant part.
No, that's right, and that's fair, and I'm not going to be able to give you a good answer in this context. In order for me to make that really meaningful, I'd really have to get down into units and friction and mass and moment of inertia, and it's a bunch of physics that's not what this course is about. So I'm going to make an assertion here. I'm going to ask you to trust me that roughly speaking, the higher category of a tornado it is, the longer the curl vector is going to be. And I'm just going to assert that and leave it to your physics and engineering professors to flesh that out. Yeah.
Is that always measured
No, you can compute curl anywhere. So curl is a formula. I mean, again, here it is. It's various partial derivatives and such, right? And so it's going to be a function of x, y, and z. Now, these are all starter examples where we're just kind of taking it easy, just nice, easy examples. And so in all of these cases, the curl has been a constant, and I've been drawing my picture at the origin just to keep it simple. But no, you point out very nicely. It does not only apply at the origin. Curl applies anywhere. Yeah.
So if your curl is constant like that, and you put the ball on the side where it's all flowing in one direction, you still have curl?
Yeah, that's right. Now, again, there's sort of a physical appeal here. But, roughly speaking, the same kind of thing will happen. And let's put it over here. And you're right that the fluid is all going the same direction, but it's going faster there and kind of slower there. And it's like then with a shopping cart at the grocery store, if you push only with your mostly with your right hand and just kind of maybe just a little bit with your left hand, your shopping cart's going to turn. Yeah. Is that cool? All right. Okay. This is really premature. The goal of what I'm going to tell you here, and we're going to flesh all this out, not fully, but certainly more later on. I just want to persuade you that these things are connected to each other. And it's pretty surprising. The way we just talked about divergence and the way we just talked about curl, they don't seem to have anything to do with each other at all. One's about rotation and one's about outwardness. You know what I mean? They seem pretty different. And likewise, neither one seems to have anything to do with gradient. Again, totally different construction. It turns out that these are extremely closely connected to each other. There's some deep water that we're going to be sort of skimming the surface of in this course. And for very deep reasons that honestly were not fully understood until less than 100 years ago. Pretty recent in the big scheme of things. It turns out that this sequence, where you compose these operators in this order, like this, very, very natural, and amazing things happen when you set it up like this. Ultimately, if you dig really, really, really deeply, and far more deeply than we're going to in this course, in fact, what you'll find is that these three operators are all special cases of the same construction. Again, wouldn't it be nice if we had time to talk about that? So what I'm going to tell you, just to kind of get you thinking about, try to get you to believe my statement here. This is what we call an exact sequence. Exact means that, as I like to say it, all lifetimes are 2. Let me show you what I mean by a lifetime. If I have some function f, and if I take its gradient, I can take its gradient, and then I get some vector field. The assertion I'm going to make here is that if I were then to take the curl of that vector field, I would get 0. And the lifetime metaphor is that 0 is kind of like death. This is a very dark metaphor, right? Sorry about that. But I think it really makes a lot of sense. 0 is kind of, if you will, sort of nothingness, right? And then think about what happens to 0 when you take the next step here and compute the divergence. 0 remains 0, right? And so it's something you can't come back from. I think the metaphor is actually kind of good. So this is what I call a lifetime of 2. That's a lifetime. So I'm going to say birth, survival, and death. All right. And what's really cool is that other than some asterisk-y kind of counterexamples, all lifetimes are 2. So, for example, if you have some vector field, and if you compute the divergence, and if you get 0, wait a second, this thing here dies here. It must have been born here, because all lifetimes are 2. Again, it's just a metaphor, right? And what would that mean? That would mean that this vector field, according to the lifetime metaphor, must be the curl of some other vector field. And that, in fact, is the conclusion here. So this theorem down here, if divergence is 0, then your vector field is the curl of something else. Again, you can just think of that as a statement about a lifetime metaphor. So there's actually a bunch of these statements. If you write them all down together, there's like 8 different statements here. I forget exactly, but there's a bunch of different versions of this. And you can, I suppose, think of them as being a bunch of independent statements about these operators and just memorize the list. But it's really easy to get them messed up and confused. It's much easier, I think, to just remember our one little metaphor, and that is all lifetimes are 2. So again, more details on this when we get into chapters 6 and 7. But what I hope I have persuaded you is that these operators, composed in this order, wow, that's pretty wild that stuff happens, nice coincidences come up, and that this is ultimately very natural. Okay, so lots to discover later on. Okay, we're done with chapter 3. Y'all have a great weekend. See you later.